Homework 19, review problems. All right, so the first one, this is really the condition that they're asking. They give us a cloud of interstellar gas. In this particular case, the gas is molecular hydrogen, which is H2. By the way, the mass of H2 would be 2. Okay, so this is the condition that we're trying to prove, or find out. Is the average temperature of the gas in this cloud less than 1/2 the escape velocity of the cloud? And it says, so if you read the problem, I'm going to read this right now. It says, in order for the interstellar cloud to contract, in other words, it starts to collapse gravitationally, the average speed of its constituent particles must be less than half the cloud's escape speed. Right? So let's figure out the escape speed, which I just did right here. I'm sorry, not the escape. Let's figure out what the average kinetic, the average velocity due to the motion. Right. So this is in some sense this velocity comes from the average temperature of the cloud. Okay. So this velocity here. I should erase this part. Right. It's not really the temperature here, but it's dependent on the temperature. Okay. So it's really the average velocity of the molecules. All right, so here, let's go back to this. Anyhow, so you got to look this up, right? So for any gas, there's this gas constant, which is 0.157 times the square root of the temperature in Kelvin divided by the mass. And so they give us the temperature in Kelvin. It's 10 Kelvin. So this is a very cold gas cloud. And they tell us to use molecular hydrogen. And so molecular hydrogen would have a mass of 0.2. And so when you do this, don't forget, you got to take the square root of, so it's the square root of 5 times 0.15. And so you get approximately 0.35, and that the answer comes out in kilometers per second. All right, so then we have to now compare that to the escape velocity. So this is not t. This is really the average. So sorry, this should actually be the average velocity. I meant to indicate that. Okay, so this is the average velocity due to the temperature of the cloud. All right, so is that, we now figured out that value, it's 0.35, is that less than half the escape velocity? So now we have to figure out the escape velocity. All right, so these are the numbers that they give us. The mass of the cloud is 1,000 times the mass of the sun, so that would be 1,000 times 2 times 10 to the 30th kilograms. So that gives us, very simply, 2 times 10 to the 33rd kilograms. All right, and then the radius is, they give us, it's approximately spherical, and it's 10 parsecs is the radius. So then you just multiply 10 times, in 1 parsec there is approximately 3.1 times 10 to the 16th meters, so that becomes 3.1 times 10 to the 17th meters. And so in this formula, this is the escape velocity formula, 2g, g is the universal gravitational constant, times the mass. The mass has to be in kilograms, which right here it is, and the radius has to be in meters, which it is right here. So I put those numbers in here, and I get, remember the answer will come out in meters per second, so I get, what did I get? Let's see. I get 927.7. So 927.7. All right, and that's of course meters per second. And so that translates, of course, to to change it into kilometers per second. It just becomes, you just move the decimal place 3 places to the left, and so that becomes 0.9, 0.9 0.93, something like that, 0.93. Okay, and that's now kilometers per second. All right, remember, we're comparing that with the answer that we got before, which was 0.35. All right, so let's let me open up a new slide here. All right, so remember, through thermal considerations, we find that the average velocity of the gas molecules inside of this interstellar cloud is 0.35 kilometers per second. We did that calculation first, and so the question is that less than half the escape speed? And so the escape speed is 0.93 approximately kilometers per second, and so you take half of that, you get 0.47. So it turns out that, of course, this number, the average velocity due to temperature, remember the temperature is very low, 10 Kelvin, is indeed less than 0.47 kilometers per second. So the answer is yes, it will collapse. Yes, all right. So, but barely, right? Because it's just barely below, right? 0.47 and 0.35. All right. All right, so here's problem 2. This is the general equation that we're going to use. So we're going to compare these two luminosities, right? The luminosity, these are actually protostars, but we can still use this equation. So it's the luminosity of the star divided by the luminosity of the sun. And so we'll compare, these two quantities. So it's really the radius of the star or protostar divided by the radius of the sun, and you square that quantity, and then of course it's the temperature of the star or protostar divided by the temperature of the sun, which of course is always 5,800 Kelvin. All right, and you raise that to the fourth power. All right, so they give us two different problems. They're talking about the Hayashi track, which is is from steps, what is it? It's steps 4 through 6, in the, anyhow. So let's get to it. So part A, so they're just giving us two completely different examples. Oh, so we have to rearrange this, and what they want to know is what's the size of the star. So remember, we're solving for our star here compared to the sun. All right, so everything else, of course, is given to us. So let me rearrange that. We're rearranging this entire equation and solving for our star. All right, so here, so this comes out to be our star. All right, if you put the other stuff on the other side here, you're going to get, this is equal to the luminosity of the star divided by the luminosity of the sun, right? Our sun, of course. And remember, because this is squared right here, we're going to have to take the square root of that, and then you get the temperature. So in you get the temperature of the sun, right? Temperature of the sun. Right, because this is in the denominator over here. The temperature of the sun divided by the temperature of the star. Sorry, this should be sun divided by the temperature of the star. And since you're taking the square root of something raised to the fourth power, you just the square root of something to the fourth power would just be raised to the second power. All right, so that's actually the equation. I just wanted to show you where this comes from. All right, so then everything else. Once you have this equation, you just plug the numbers in. For part A, the numbers are, what is it, 5,000, so the luminosity of the star is 5,000 times, no, not 5,000, oh yeah, it is 5,000, okay, so it's going to be the square root of 5,000 divided by 1, right, because that's the luminosity of our sun is 1. And then we compare the temperatures, right? So the temperature, remember you have to do what's in parentheses first, right? So it's going to be it's always the temperature of the sun, 5,800, that's 5,800, divided by, and they gave us the temperature of this protostar as 3,500. All right. So remember, do the fraction first and then square it, and then you multiply by the square root of 500. When you do that, I get 100, so this tells you the size of this protostar compared to our sun, 194. So this whole thing is times the, so this is divided by the radius of the sun, right? So you bring that over, and then this is times the radius of the sun. All right, so I didn't mean to use a capital R there, sorry about that. Anyhow, so this protostar is 194 times the radius of the sun. All right, let's do part B. All right, the conditions that they give us for the second one, you've got a protostar that's three times the luminosity of the sun, so it's 3 divided by 1, and now it's 5,000 Kelvin, so it's the temperature of the sun divided by 5,000, but you square that fraction and you multiply by the square root of 3, which turns out that this protostar is now it's actually just about to become a star, is 2.33 times the size of our sun. All right, so that's problem number 2. All right, so this is number 3. Let me finish writing this. So this is going to be the temperature at stage 6 divided by the temperature of stage 4, and of course we have to raise that to the 4th power. All right, so this is the let me read it. Use the radius luminosity temperature relationship. Right, that's what I just wrote. To explain how a protostar's luminosity changes as it moves from stage 4 to stage 6, and they give us the temperature and the size of the star in stage 4 and then in stage 6. Okay, and so they want to know what this change in absolute magnitude is. So we just need to know what this ratio is, or this fraction is, of the luminosity in stage 6 to the luminosity in stage 4. All right, so we're going to plug the numbers in here, and we get, so this is going to be, so I'm just using the numbers that they gave us. Let's see, it's 10 to the 6th divided by 2 times 10 to the, so 10 to the 6th. 10 to the 6th. This is in kilometers, and the denominator is also in kilometers. 2 times 10 to the 8th. All right, so they gave us this in the problem. And remember, we're squaring that fraction, and then the temperature is going to be 4,500 divided by 3,000. 4,500. That's supposed to be a 5. 4,500 divided by 3,000. Right, again, this is just given to us in the problem, and then you raise that fraction to the 4th power. So then we get what L6 to L4 is, right? So this tells us that L6, the luminosity in stage 6 to the luminosity in stage 4, right? Is going to equal, let's see, so what does it turn out to be? It is 1.27 times 10 to the minus 4th. 1.27 times 10 to the minus 4th. Times 10 to the minus 4th. All right. And so another way of doing this, I mean, this is basically the same thing. If I were to change this into a whole number, it turns out that it turns out it's better to do it this way, or just it doesn't really matter. This is also equal to 1 over 7,901. Right, you just take the inverse of this number, and that's what that turns out to be. All right, so it just, you'll see why I did that. All right, so let's continue this problem. All right, so.